Okay. Никого и нет. А вот тут есть. Today I will have a quality April Fool's class. All right, so I'll open the chat, but I just want to remind you that if you press space, you'll get unmuted. So if you want to ask something, you don't need to write it in the chat. You can unmute yourself and ask by voice. All right, yep. So, so I promised to do some homework problems today. So let me open the homework first. It was homework 7. Here we go. Yeah, so let's remind ourselves what's Laurent series and do some Laurent series. Looking at my camera. Okay, so homework. And okay, so for the newcomers, a reminder that if you want to ask a question, you can do it in chat, but you can also unmute yourself by pressing space. Okay. So, yeah, so homework. Sorry, we're figuring out homeschooling here, which is even harder than complex analysis. Okay, so Laurent series for e to the z divided by z plus 1 squared. Okay, so first thing is that we identify where is the problem. So the problem is at z equal to -1. Okay, so otherwise our function is analytic, and so Laurent series don't make sense. So the only thing that makes sense is z equal to -1. Like the only point at which Laurent series makes sense is -1. Okay, 10 seconds. Вика, я тебе разрешу посидеть ровно 5 минут, потом ты пойдешь дальше заниматься. Хорошо? Okay. Sorry. Okay, so at z equal to -1, well, z plus 1 square is already of this Laurent type. And so we only need to expand e to the z. So our goal is to write e to the z as Laurent series. So series centered at z equal to -1. Now, e to the z is analytic everywhere. And because e to the z is analytic everywhere, this series will be actually Taylor. So my point is that we'll have something like this. Okay, plus so on. And then after, plus 1, sorry. And then after we achieve this, we divide it by z plus 1 square. And we'll get the Laurent series. And in particular, we see how many Laurent type terms we'll get. So we'll have something like this. Okay, by the way, I'll zoom out a little bit. So our only goal in problem 1 is to write this expansion. Now there are several ways to write this expansion. One is to multiply and divide by e to the z. But we can actually do it simpler just by differentiating. So remember that an is equal to the nth derivative at our point, in this case at -1, divided by n factorial. And in this case, finding nth derivative is easy, because the nth derivative of e to the z, so e to the z and derivative is still e to the z. So at -1, we get e to the -1 always, which is 1 over e. And so an is just 1 over e divided by n factorial. And so we get that e to the z is equal to 1 over e times 1 over e plus 1 over e times z plus 1 plus 1 over e times 1 over 2 factorial, which is 1/2 z plus 1 square, and plus so on. In particular, we can factor 1 over e out, and then we just get the sum of z plus 1 to the power n divided by n factorial, and starts from 0. And then we need to divide by z plus 1 square. So e to the z divided by z plus 1 square. So either you use this, either use this first line and just write several terms and then plus ... or you can use this formula. I'll use this formula. So it's 1 over e times the sum z plus 1 to the power n minus 2 divided by n factorial. And then we can shift n, like instead of n minus 2, we can write n, but like anything is okay here. The most important thing for us, because now we know that we're using this for integration, is to see the pole. And the pole, like the residue will be here. So the residue will be a1, and we know that a1 is just 1 over e. Okay, it freezes a tiny bit, so if it freezes badly, say something or write in chat. Okay, so problem number 2 is something you've seen in calculus a lot. It's to write the series for 1 over 1 minus z square by differentiating. So how do we do it? We write the series for 1 over 1 minus z at 0. So it's just z to the n, and from 0 to infinity. And then we realize that 1 divided by 1 minus z square, and this is the most important thing in the problem actually, is to realize that we don't need any minuses. That 1 divided by 1 minus z square is the derivative of 1 divided by 1 minus z. So there is one minus coming from the fact that we're differentiating the denominator, but then there's another minus coming out of the chain rule here, and so in total there are no minuses. Okay, so we need to differentiate the series, and so n just comes down, and we get this. And a good thing to notice here is that the term that corresponds to n equal to 0 actually disappears. So if you look at the term that corresponds to n equal to 0, it will be 0 times 1 over z. And this 1 over z would make us really sad because it's not analytic at 0 anymore. But fortunately, it doesn't make us sad at all because it's multiplied by 0. So for the last thing, I want to write the same sum, but starting at 1. Okay, and then the second part of the problem is to write the series for 1 over z square. So to get 1 over z square, sorry, my eraser tool disappeared. So for 1 over z squared, we take 1 divided by 1 minus z squared and plug z instead of 1 minus z. So it means that we want to replace 1 minus z by z. And replacing z with 1 minus z is the same, which is the same as to plug z, plug 1 minus z instead of z. Because if you take 1 minus z and plug 1 minus z instead of z, you will get z. So that's something from calculus. Again, it's always a mess. So let's see how it's going to work out. So we know that 1 over 1 minus z squared is sum n times z to the n minus 1. And so 1 over z squared. So every time I see a z, I need to plug 1 minus z. Now, theoretically, this is not exactly the Laurent series, because in Laurent series, we want to have z minus 1 instead of 1 minus z. So let's do it. And we'll get this. Now, I didn't grade the homework yet, but I won't take any points off for these little things, okay? I'm actually surprised that none of you asked, but I won't take any points off for not doing this, for example. And I definitely won't take any points off for not doing this. These are really very small things. But again, theoretically, like to have the most beautiful answer, this has to be done. All right, so number 3. So number 3 is terrible. Number 3 is called exercise in opening parentheses. So for problem 3, we just need to write enough terms everywhere. So, okay, so first of all, no. Yeah, okay. Let's just start like this. So I know that this is e to the z. And now for z squared plus 1, we need to use the ideas from the previous problem. So we have already done 1 over 1 minus z. So I'll write it this, and this is super ugly. But I can now use the previous problem because I know what's 1 over 1 minus z. It's this. And now if I want minus z squared instead of z, I just do this. You did this in calculus a lot, by the way, when you did series for arctangent. Series for arctangent goes exactly like this. Okay, and I'll write first couple of terms. So it will be 1 minus z squared plus z to the 4th minus z to the 6th, and so on. Okay, and then the last thing is 1 over z, but 1 over z is fine. Okay, now I want to take this and multiply. And theoretically, so I need only 4 terms. So taking 4 terms here and 4 terms here should be enough. Theoretically, I can give an example where there won't be enough because we'll have 0 terms, but here everything will be fine. So that's not an example to completely torture you. Okay, so let's take this one and multiply. So we get 1 minus z squared plus z to the 4th minus z to the 6th. Then take this z plus z minus z cubed plus z to the 5th minus z to the 7th. Now this plus z squared over 2 minus z to the 4th over 2 plus z to the 6th over 2 minus z to the 8th over 2. And finally z cubed over 6 minus z to the 5th over 6 plus z to the 7th over 6 minus z to the 9th over 6. Now, we need to stop and take a deep breath here. We need to stop and take a deep breath because we need to remember what the problem was about. The problem was about the first 2 terms. So my first 2 terms will have powers 1 z squared and 1 z squared and z cubed, and nothing else, unless they cancel out. But here they will not. So I'm in particular not interested in this, 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 and in this, and in this, and in this. So I'm interested only in the terms that didn't get circled, because I need the first 4 terms. So I have 1, I have plus z, I have minus z squared plus z squared over 2, which is minus z squared over 2, and then I have, then I have minus z cubed plus z cubed over 6, which is minus 5 z cubed over 6. Plus on. So these are my 4 terms, and then we recall that we actually didn't need this. We needed this divided by z also. Yes, I assume you know what the problem is because from the homework. So, but anyway, I need to take this and divide by z. This is what the problem was about. And these are the 4 terms I'm getting. But what this problem emphasizes is that, like, if you want to work extra hard, then you can write as many terms as you need. So, like, if I needed 10 terms, I would do 10 terms. I would just have to very carefully write all these terms in the 2 expansions here. But again, theoretically, we can write as many terms as we want. All right, so problem number 4 was about residues. We have some proficiency in residues. Now let me do problem 4, part 3. So it asked for, the residue of z minus sine of z divided by z. So let's do this. I want to do this because there will be this funny cancellation. So sine of z, and we know, by the way, that without the z, that this function doesn't have a residue. So let's see if this does. So sine of z looks like this. So sine of z minus z looks like this. And so sine of z minus z divided by z looks like this. By the way, now we have more tools to compute residues. So now we didn't even need power series probably. But this is still nice because this emphasizes that not only we don't have any residue, so there is no residue here, there is no 1 over z, but in fact, this function is 0 at 0, its derivative is 0 at 0, and only its second derivative is what? Is minus 1/3 at 0. So this is actually a very nice analytic function. And yeah, so for the rest, we have some strategies. Okay, and then, okay, I'll skip problem number 6. We did something related to number 6 a lot. Let's choose something from problem number 5. Let's, for example, you know what? I'm going to do the second one, I guess. And we are evaluating it around the circle with absolute value of z equal to 3. So what is our problem? Our problem is at 1. So we need the residue at z equal to 1. And that's a nice problem because we can kind of use the strategy from problem number 1, right? So in problem number 1, we wrote series at -1. So now we need to write the series at z equal to 1, but for e to the minus z. Okay, so let's denote phi of z equal to e to the minus z. And I know that phi of z is equal to this sum. So it's phi of 1 plus phi prime of 1 times z minus 1 plus phi prime prime of 1 z minus 1 square over 2 plus so on. So we need the residue only. Okay, we need the residue at z equal to 1. So let's see what we will be getting. I'll get phi of 1 divided by z minus 1 square plus this plus on, and here is the residue. So the residue is what we have at the power -1. And so we only need to find phi prime of 1. Let's see, yeah, I have this function. So this is phi prime of 1, and phi prime of z is minus e to the minus z. So phi prime of 1 is minus e to the minus 1. And so the answer is that this integral is equal to 2 pi I times minus e to the minus 1. So minus 2 pi I divided by e. Okay, so that's that was the homework. Okay, sorry, definitely not getting enough sleep these days. Okay, so now we need to continue with our real valued integrals. And there is one thing we need to learn. And it's called indented paths. Yeah, by the way, any questions about the homework? Reminder, you press space, it unmutes you. So you hold space and speak. If you have any questions, you can feel free to interrupt me anytime because I cannot see your faces. Oh, I see. Thumbs up. Yes, I cannot see your faces, so your best shot is just to interrupt me whenever you have a question. Okay, so what's an indented path? So we will have in mind our example with this integral, which I advertised many times by now and never computed, sine of x divided by x. And we saw last time how to deal with trig integrals. We replace sine with e to the ix, and then we're going to need the imaginary part. And then we need this contour, okay, our CR. Unfortunately, however, there is one problem. The pole of this function, is not inside the contour, it's right on the contour, because this function has a pole at 0. Okay? And this is forbidden. We can never allow our function to be bad on the boundary of the contour. We always assume the function is good, like somewhere around the contour. And to avoid this, we will modify the contour a little bit. We'll come close to this point, and then we will go around it like this. A good question is, why didn't we go around it like this to have the pole inside the contour? It actually doesn't matter. It would also work, but it doesn't really matter. The actual answer is that I want to stay above x-axis at all times, because we've seen that staying above x-axis is actually nice. Now, we need to be really careful about the orientation. So our contour is oriented like this. In particular, this, we will call it C sub epsilon. This is the circle absolute value of z equal to epsilon. Or you know what? I'll actually call it gamma sub epsilon. That's a Greek letter gamma, and incidentally, it's also a Russian letter G. I'll call it gamma because C is taken, and C usually means the circle plus the horizontal parts. So I don't want to use C for two different things. Okay. And this gamma epsilon will be oriented clockwise, which is generally bad, but here we don't have any other choice because we want to go counterclockwise over the whole contour, so I want to move in this direction. Okay, I have too many things on my screen and eventually I'm not seeing what you're seeing. Yeah, so I want to go in this direction, kind of. And this forces us to orient this little fellow clockwise. Okay, so this will be my new CR. So new CR, I have too many pictures there, is this. It's like a rainbow. And the good thing is that this sine of x divided by x doesn't have any poles inside. So the residue theorem will tell me that if I integrate, or e to the ix, the residue theorem will tell me that if I integrate e to the iz divided by z over this new CR, I'll get a 0. And now let's split this integral. So it will be the integral over this big one plus the integral over like this first horizontal line plus the integral over this small, and this should be oriented differently. Messed up again. And plus the integral over the second horizontal thing. Now the hope is that this will go to 0. The next hope is that these two integrals together will approximately be the integral from minus r to r. Because at the end of the day, this is minus r, this is minus epsilon, this is epsilon, and this is r. And this small horizontal part shouldn't be too bad. But the question is, what is this? So what is the integral over this very, very small path? Will it be 0? Well, the answer is no, it won't. And it won't be 0 because f is bad. So f has a pole, f has a singularity very close to this path. So even though the path itself is small, but the f on this path is big enough to kill the smallness. And there's a very important theorem here. So I'll state it and then we'll continue with this example. So theorem goes like this. So assume, just a second. Yeah, that's better. Assume f of z has, a simple pole at z equal to x0 on real axis. With residue, okay, the book calls it B0, so let's call it B0. Okay, so I won't enumerate book enumerates assumptions. So assume also gamma epsilon is the upper half of the circle z minus x0 is less or is equal to epsilon. So the picture is this. So here's x0 and here's gamma epsilon. So this is a circle of radius epsilon that goes around x0 and we only take the upper half. And we also assume that it's oriented weirdly, and what does weirdly means clockwise. So oriented this way. Because no, sorry. The other way. See, I can't even properly draw. I can't. Yeah. It was actually correct. Curiously, so I can't properly draw a clockwise orientation, but I got confused because clockwise is very anti-intuitive. Okay, then I'll write the then, and then I'll show you the whole statement. Then limit of these integrals as epsilon goes to 0 is minus pi I b0. So here's the whole statement. And I don't want to prove it, but I want to explain why is it trustworthy. Okay, so why is it trustworthy? Because we know that if we went the full circle around x0, and this circle was oriented decently, which is counterclockwise, then the answer would be 2 pi I times the residue. Now we orient the circle differently, we orient it clockwise, and this is y minus. So the only other thing that disappeared is the 2. Why did it disappear? Well, because we only have half of the circle. So we have half of the circle, which means that we have half of the answer. So for the whole circle, we get 2 pi I. What's going on? And for half of the circle, we get pi I. Oriented clockwise, which is this way. Now, of course, I'm cheating. Of course, you can challenge me and say, well, taking half of the circle doesn't mean that we're getting half of the answer. Maybe a bigger portion of f was on this top part and blah, blah, blah. But in fact, if we do everything carefully, we will see that it's fine. And I don't want to do anything carefully, and you don't want me to do anything carefully because it will again involve tons of estimates. So let's just go with this kindergarten explanation that if we had the full circle, we would have the pi, and if we have half of the circle, we're only getting half of the answer. Okay, and now example. So now finally, I'm going to do this carefully. So we'll introduce f of z is equal to e to the iz over z. And before I start anything, I want to say that Jordan's lemma applies for CR. Because what did Jordan's lemma say? Jordan's lemma said that if we're integrating exponential times something small, then over CR, the limit will be 0. Well, we have the exponential divided by z. And on this circle CR, z becomes super huge. And so 1 over z becomes super small. And so Jordan's lemma applies. And it means that on CR we'll have absolutely no problem. Now, for CR, let me be a little bit more careful. For the top part of CR. For this part of CR, I meant. Now let's draw the whole CR. So as I promised, CR will be this, will be the rainbow. So this is equal to R, this is equal to epsilon, and these are the real parts. And we know that inside CR, F is analytic. I'll show you F again. Here's F. It has only one problem. It has a problem at 0. But because we went around 0 like this, it means that in CR we are analytic, and this implies that the integral of f of z dz over CR is 0. All right, so 0 is equal to the integral over CR f of z dz, which is equal to the integral over z equal to r, plus the integral over this part. And this part is what? It's the integral from minus r to minus epsilon e to the ix over x dx. So that's the kind of real, not real valued, but real variable integral. Because on this part of my contour, z is actually real, and this is minus r, and this is minus epsilon. So z goes from minus r to minus epsilon, plus the integral over this part, and plus the integral from epsilon to r. So here, okay, and I need one extra comment that this is clockwise. I always need to keep track of the orientation. That's very important. Otherwise, I lose a sign. Otherwise, I lose a light. So this first, so now eventually I'll pass to the limit. Okay, I'll pass the limit, and this will go to 0. So I'm passing to the limit first as r goes to infinity. So this goes to 0. This is Jordan's lemma. And this I said already, discussed, kind of discussed that Jordan's lemma applies. So this first term disappears. What happens to the second term? When r goes to infinity, we just replace r with minus infinity. Ix over x. Okay, this integral is still the same. This third integral didn't depend on r at all. And this final integral will be from epsilon to infinity. So any questions so far? I'll now take the limit as epsilon goes to 0. But if you have any questions about eliminating r, okay, never thumbs up. Only one though. All right, so let's eliminate epsilon. Let's send epsilon to 0. Now, one important thing I want to say is that I'm not doing any convergence. So let's assume that every integral I give you will converge nicely. So convergence is a completely different story, which I don't really want to touch. In particular, here everything will converge. Okay, so when I send epsilon to 0, this just becomes the integral from minus infinity to 0. Okay, plus this limit. And this limit is exactly what we had in our theorem. And now we need to realize that these two integrals add together and give me an integral from minus infinity to plus infinity. Because I have from minus infinity to 0 plus from 0 to infinity. So this is what I'm looking for. And what is this? Well, this is exactly minus pi I times b0, where b0 is the residue of f of z at 0. Because let's go a little bit earlier. Here it is, here it is, here it is. It's exactly this equality. Okay, this was a horrible error, but that's an error. It points to this equality and I'm using it right here. So my final goal, oops, is to find b0. Well, it's not hard. So it's just 1, right? Yes, yeah. It's so we're gonna have this p of z divided by q of z. Okay, just a second, I'll answer the question. So this is going to be 1, and so this is going to be minus pi I. Pi I goes to the left hand side. Okay, why are some of the integrals using complex? Good question. So I can use complex variable everywhere, but I'll just draw another picture here. So recall what our path was. Our path looks something like this. And where are the x's? Well, here are the x-axis, right? So, okay, now it will become super colorful. I like it. So this part of the path and this part of the path lies strictly on x-axis. Okay, so we formally still have the complex variable here, but z here and z here looks like x plus I times 0. So when we're on this part that's highlighted in blue, z is real. Nowhere else is z real. So on this circle, z is not real. Okay, on this circle, z looks like r times cosine theta plus I sine theta. And this imaginary part is not 0. On this circle, z looks like epsilon times cosine theta plus I sine theta. And it is not real again. So the only two places where z is real are highlighted. And now I'll scroll back and you'll see that I'm using the real variable only on these two parts of the path. So only here and here. So here and here, I'm allowed to write x instead of z because the imaginary part of z is 0. Now, here and here, I'm not allowed to do this because here, imaginary part of z is not 0, and so z is effectively complex. By effectively, I mean that it's not only formally complex, like any real number is also a complex number, but it's complex in the sense that it does have a non-zero imaginary part. So did I answer? Yeah, you can also press space and say, yes, you did a great job. Or something different. So yeah, so the way to tell is that you look at the picture, and if you see that your z runs like around real axis, then not around, sorry, if z runs over real axis, then you're allowed to write x instead of z. If z stays on some weird semicircle, sorry, then you keep it complex. Okay, so back here, so we figured out that the residue is 1, so we get minus pi I here. So what we got is that 0 is equal to the integral we're looking for. Minus pi I. So our integral e to the ix over x dx is equal to pi I. And so the integral of sine of x over x is equal to the imaginary part of this first integral, so imaginary part of pi I, and this is pi. And that's my big achievement today, that I finally showed you how to compute this integral. This is a really important integral. You see it in many places. I'm pretty sure that in engineering, you see it too. This is one of these integrals that, one of these functions that oscillates like crazy, and you see this in engineering occasionally. So the answer is pi, and the funny thing is that I don't know any other way to compute this integral except using complex analysis. So that's an important example of an integral that you cannot compute differently. Okay, so I have 1 more minute, and I'll finish kind of extending my answer to this really important question: when do we use complex variables and where do we use real variables? So the general strategy is to use real variables, is to have z be real whenever possible, and somehow eliminate all the parts of the contour when z is not real. So on Monday, everything where z wasn't real just went to 0. And here, not only to 0, so here we have different answer for the small part of the contour. But this question is particularly good because you do need to keep track of when z is real and when z is not. So typically, like the parts of the contour where z is real will give you the integral you want. And parts of the contour when z is not real will either disappear completely, or disappear because of this minus pi I theorem. Okay, so we are done for today. We will continue exercising in residues, and then we'll probably have some more time in the course, so we will do a little bit of conformal mappings. But the good news is that we're almost done with like the main objectives of this course. So the rest of our struggle should be hopefully a little bit less painful, because you will know that the main objectives of this course are met. Okay. Thank you. Yeah, she's, you'll see her more, probably because the schools are canceled until May 1st at least. So she'll be around. Okay, so yeah, so I'll see you all on Friday, and I've sent the homework yesterday, so most of it is extra credit. So hopefully you'll be able to improve your scores and be happy with the scores eventually. So see you on Friday.